Okay, hi everyone. So yeah, my name is Jason Murphy from Analog Devices. So I've been with ADI for about 4 years in total. My background is in embedded software and system development in the domain of industrial automation primarily. So working on technologies in the building automation space, industrial connectivity. And for I guess about a year or so now, I've been working with Zephyr, primarily in the context of single pair Ethernet. So that's what today's talk is going to be about, enabling real-time secure connectivity to the edge with single pair Ethernet and Zephyr OS. So just for an agenda for this talk, I'm going to kick off with an intro to 10BASE-T1L, single pair Ethernet. I'll discuss this technology, what it's all about, the use cases, and why you might consider using it for a project or a device. We'll then look at the importance of software and the need for software when developing solutions and devices based on 10BASE-T1L connectivity. And then look at Zephyr and look at why Zephyr is a great choice when developing these types of applications. Okay. So let me begin with some background into this technology and why it exists. So I guess I'm sure everyone here is pretty much familiar with the concept of Industry 4.0, the digitalization of industrial, factory and building automation environments. And so in general, there's a demand for more interconnected devices and data-driven decision-making. As you can imagine, industrial networks play a very important role here in facilitating this. And over the last number of decades, Ethernet has been adopted in these industrial networks where possible as a standardized communication technology. So while Ethernet has been adopted where possible in these networks, primarily at the backbone of these networks at what's known as the control level and at the enterprise level, as you see on the slide here, a gap existed in bringing Ethernet to the edge. And so in 2019, the IEEE ratified the 802.3 CG standard for 10BASE-T1L single pair Ethernet, which is a new physical layer standard defined really in enabling Ethernet connectivity to edge devices. So what is 10BASE-T1L? Well, you can summarize it with 4 key things really. It's 10 megabit per second Ethernet that operates over distances up to 1 kilometer that can also carry power and data and all over a single twisted pair of cabling. So that's just 2 wires. So the image on the right side there shows, I guess, a representation of where 10BASE-T1L would sit in a typical industrial network. So like I said, while your backbone, your enterprise and cloud and control levels will remain with standard and gigabit industrial Ethernet, as this Ethernet network extends to the far reaches of industrial environments, think sensor and actuator type devices, 10BASE-T1L extends that physical layer to these types of devices. So the result really is a network that converges completely on Ethernet with a seamless link from the edge to the cloud. So just to go into some more detail about 10BASE-T1L and the key benefits of this technology. So I'm going to look at this in 4 key areas, including data rate or throughput, bringing IP to the edge, security and diagnostics. So with data rate, so 10 megabits per second, you're probably saying, we have gigabit Ethernet these days, it's nothing impressive. The key thing to consider here is the comparison to the legacy fieldbus protocols which 10BASE-T1L is replacing. So if you consider a technology such as RS-485, for example, a serial bus, over distances of like 1 kilometer, RS-485 would be operating in the kilobit per second range. So 10 megabits per second is a sizable improvement here, and there's oftentimes plenty of data rate for type sensor type and edge device applications. The improved latency is also important for applications where low latency networking is critical, such as control loops where there is often a desire for millisecond latency. The next thing is IP to the edge. So this really is a key factor with 10BASE-T1L. I mentioned the converging of networks on Ethernet throughout. So with 10BASE-T1L, the entire industrial network can converge on Ethernet connectivity all the way from your enterprise cloud level down to your edge devices. As it stands, industrial networks are often fragmented in that there's varying technologies used throughout, which requires complex translation systems and gateways to convert between these technologies, which results in siloed data or data islands. By moving towards Ethernet, the entire network can converge on Ethernet and really simplifies data access throughout. Next is security. So again, in the industrial space, as the IT world and the OT world, which is the operational technology, or so factory floor technology, let's think about it like that. As these technologies converge, security becomes increasingly important because, as you can imagine, the ability for external attackers to access this OT technology through the IT domain increases. Thus, it is really important that modern cybersecurity techniques are deployed to the operational network. And then finally, diagnostics. The key thing here is that Ethernet is full duplex connectivity. Again, in comparison to the legacy fieldbus protocols like RS-485, these protocols are often limited. They're half duplex, can only send limited amounts of data at one time. With Ethernet, we open the door to more complex data, device-centric data being sent, such as device data, diagnostic data, and even implementing features such as over-the-air updates, or I guess over-the-wire updates. Okay, so at ADI we have a portfolio of 10BASE-T1L transceiver products. There's 3 in total. So just to quickly highlight what these are, and to give context to, I guess, the software piece, there is a PHY, a MAC PHY, and a 2-port switch. So each, I guess, has a slightly different use case and application depending on what you're trying to do. The PHY will be primarily used in more high-performance applications where a more high-performance processor is in place. The requirement here is that your processor has an onboard Ethernet MAC. And so the interface between the processor and this PHY will be done using RMII. I guess what I want to talk more about today is the MAC PHY and the 2-port switch products. With these products, they include an onboard Ethernet MAC, and the interface to the microcontroller is done using SPI. So this opens the doors to adding 10BASE-T1L single-pair Ethernet connectivity to simple microcontroller type devices, ARM Cortex M0, M4, pretty simple MCUs that do not include an onboard Ethernet MAC. And really that's kind of what I want to talk about today in the context of Zephyr. Okay, so while we have these 10BASE-T1L transceiver PHYs and MAC PHYs, enabling an embedded device with Ethernet goes beyond the physical layer. And, it can be a challenge to do so. When we consider the OSI model that represents the layers in a networking stack, we see that the Ethernet standard itself defines only the physical and data link layers. And everything from layer 3 upwards is purely software defined. So that kind of gives you an insight into the importance of that software plays. Outside of this, key connectivity, key software components include things like device drivers for communicating between the host processor and the PHY or MAC PHY. The connectivity stack, and this is again a key requirement from a software standpoint. The TCP/IP suite is pretty much the de facto standard when it comes to implementing networking connectivity these days, and it's vitally important that embedded devices have a full TCP/IP stack to ensure that they are interoperable with existing IP networks. Next is application protocols. So this would be application dependent, but common application protocols like MQTT, HTTP, CoAP, lightweight M2M, again, are all software defined. And finally, there's also a trend, generally speaking, towards carrying out more processing at the edge, so decentralizing software. And so it's something to consider that these edge devices are being tasked with increasing processing loads. So that's where our friend Zephyr enters the equation. Really, I see Zephyr as a highly suitable embedded software ecosystem to enable the development of embedded systems and devices with 10BASE-T1L connectivity. So I'm going to go ahead now and look at why Zephyr is a good choice, and then look at how 10BASE-T1L is supported within Zephyr and how you can develop applications with Zephyr and 10BASE-T1L. Okay, so why Zephyr? Well, there's a couple of reasons for this. I think generally speaking, people associate Zephyr with wireless communication most prominently. Zephyr is highly prominent in the IoT domain with wireless technologies like Wi-Fi, LoRa, Bluetooth, etc. But primarily the same software can be deployed for wired applications also. And this is very true of the TCP/IP networking stack that Zephyr provides. So this stack provides support for the key protocols required when enabling a device with Ethernet connectivity. from layer 3, layer 4 network transport layers all the way to various support for layer 7 application protocols. Zephyr's stack is also native, meaning that it was developed specifically for Zephyr, with common memory buffers being used throughout, which is advantageous in terms of reducing RAM usage, which can be an issue when implementing TCP/IP connectivity on embedded devices. The real-time performance is also a factor to consider. So Zephyr obviously is an RTOS, and while it's not always a hard requirement to have real-time capabilities on embedded systems like this, implementing low latency networking is often a requirement for industrial applications. So Zephyr provides those capabilities. Resource efficiency is also it's a factor in lots of embedded systems, but again, when you're considering pushing connectivity to the edge where you have a simple MCU, ARM Cortex M0, M4 with limited RAM and flash, resource efficiency is critical. So Zephyr is highly optimized for these types of applications. And then security. So I've touched on the importance of security. As the IT and OT domains converge, it's very important that modern security techniques in terms of data encryption over the Ethernet link as well as device authentication are deployed. And again, Zephyr provides all the key components here. And then being open source and being portable are things that aren't specific to this application but are obviously very nice to have. From a portability perspective, I think that the ability to reuse application code, networking application code, that's agnostic to the physical layer. So for example, the ability to reuse application code that was developed for a Wi-Fi physical layer with Ethernet is highly advantageous. Okay, so now I want to look at how 10BASE-T1L is supported within Zephyr. And so, like I said, Zephyr is more associated generally with wireless communication, but it does have quite a good level of support in place for Ethernet. And so Zephyr defines a standard layer 1 API for Ethernet devices. So supporting the 10BASE-T1L physical layer, supporting a 10BASE-T1L transceiver in Zephyr is really just a case of implementing the standard layer 1 API. And this abstracts away all of the common and the complex details of the physical layer away from the upper layers of Zephyr's networking stack. So just the image on the right side shows the interface between the host MCU and the MAC-PHY. There is a standard 4Y SPI interface along with 2 GPIO pins for interrupt processing and to reset the device. So the standard API is shown here on the slide. It's a pretty simple API, generally speaking. There's APIs to start and stop the interface, to get its hardware capabilities. So this is information pertaining to the physical layer, like its throughput, if it's 10 megabit, 100 megabit, etc. If it supports promiscuous modes, auto negotiation, for example. There's an API to set the config of the device, and then finally to actually send data to the physical layer. So really, supporting a 10BASE-T1L transceiver within Zephyr is a case of implementing a driver which defines these APIs. The initialization function, I took a snippet here from the ADIN 2111 driver from Zephyr. And so the key things that this type of driver function will do will be to check the SPI interface between the MCU and the MAC-PHY, configure, reset, and interrupt GPIOs. So these will have associated callback functions which will be used to handle data being received over the physical layer, a soft reset, and then finally creating an offload thread. So a common approach within Zephyr Ethernet drivers is to create dedicated threads in the driver layer which will be responsible for handling data received over the physical layer. These threads will be synchronized on interrupts from the device, which will then allow the thread to go ahead and read data from the receiving FIFOs. Okay. In the context also of driver support for these devices within Zephyr, I want to highlight a recent addition to Zephyr, which was recently merged upstream in the past couple of months, and this is support for the Open Alliance SPI interface. So Open Alliance is a kind of special interest group which is really focused on pushing the use of Ethernet in industrial and automotive applications. So this special interest group defined a standard 10BASE-T1X MAC-PHY serial interface. So T1X means that it supports both 10BASE-T1L long-range Ethernet as well as 10BASE-T1S short-range Ethernet, which is primarily used in automotive applications. The benefit of this MAC-PHY interface is that it enables full 10 megabits per second frame transfer with an SPI clock of around 12 to 16 megahertz. So to achieve full 10 megabits per second frame transfer using standard SPI would require your host processor to operate its SPI peripheral with a frequency of near 25 megahertz. So having support for this Open Alliance SPI within Zephyr is great to see. It's great to see that there is, the open source community are out there and using 10BASE-T1X. Okay, so then now let's look at Ethernet application development within Zephyr for 10BASE-T1L. And so there's four key points to this, four key things that one must do. These are platform selection, board config or hardware config, software configuration, and then finally moving to application development. So first up is platform selection. So there is currently support for two of ADI's 10BASE-T1L transceivers within Zephyr. These are the ADIN 1110 MAC-PHY as well as the ADIN 2111 two-port switch. So these transceivers, along with their respective evaluation kits, are supported within upstream Zephyr. You can see their location in the drivers directory. So these evaluation kits have onboard STM32L4 MCUs with some things like temperature sensors, for example, which are useful when developing kind of proof of concept applications. So these boards will be a great starting point for developers looking to get started with 10BASE-T1L within Zephyr. Of course, you have the option to interface to any host processor of your choice using the exposed SPI headers on these boards. So once you choose your platform, next up is device tree configuration. So I've included a snippet here from device tree for the ADIN 1110 MAC-PHY, and so for those familiar with device tree, there's nothing new here, but the key things we're configuring are the SPI interface, the SPI bus we are using, the reset and interrupt pin configuration, the SPI frequency, along with the DMA config if DMA is being used. And obviously using DMA in an application like this where we're frequently reading and writing to the SPI bus will be advantageous. The MAC address of the device is also specified here in device tree, as well as the Ethernet LED functionality. So these MAC-PHY products have onboard LED GPIOs, which can be used to signify things like the traffic on the network. So once device tree config is done, we move to software config using kconfig. And really here it's a case of choosing your protocols that you want to use in your Zephyr application with Ethernet. The key kconfig symbols that must be defined for Ethernet support are shown here in the box. So Ethernet driver layer, the support for the ADIN driver part itself, as well as the layer 2 API for Ethernet. And everything beyond this really is application dependent, be it you're using IPv4, IPv6 or both. You may use TCP or UDP. In this case, we're using DHCP also, along with sockets and MQTT connectivity. So as you can see, Zephyr supports many of the key layer 2, layer 3, and layer 4 protocols, which are important when developing applications with Ethernet. Okay, so then after that, you're free to move to application development. So for those who have worked with Zephyr, Zephyr's networking stack for be it with Wi-Fi or 802.15.4, whatever physical layer, the same APIs and libraries can be deployed with single pair Ethernet, so nothing changes here. And I think this is kind of one of the beauties of Zephyr, the ability to reuse code across different physical layers without the need for much porting. So Zephyr has support for the BSD socket API, MQTT, HTTP, lightweight M2M, and CoAP. Again, lots of these are highly industrial focused, which is great in the context of 10BASE-T1L. I think for developers also who are looking to move to maybe working on a product with industrial connectivity, who have experience with socket programming, this opens the doors to reuse your existing knowledge, your existing know-how with socket programming or MQTT, for example, with an industrial focused communication technology. Other protocols that Zephyr supports, which are really useful for these types of applications, are things like DNS, DHCP, the JSON library, which is important when communicating with the cloud. The network management library is great for when developing, for handling networking events that happen throughout the program. And then zperf is great for managing throughput and measurement of latency of your network. Okay. I also want to highlight securing Ethernet connectivity. So Zephyr provides support for the TLS protocol using embed TLS. Like I touched on earlier, the importance of TLS is there, given the importance of security in the IT, as the IT and OT domains are converging. Zephyr makes it really easy to enable TLS security over Ethernet using standardized APIs. If you've ever tried, spend time configuring embed TLS outside of Zephyr in the bare metal environment, and spend time, integrating it with a TCP/IP stack, etc., having this pre-integrated and the ability to move directly to application code development is very, very valuable. Okay, so just want to highlight an application that I've spent some time working on recently. So I currently have a PR open to merge this as a sample application upstream. It's really serves as a reference design for customers looking to get started on 10BASE-T1L connectivity. So I've tested this on the eval kit for the ADIN 1110, and it really pulls together software with some of Zephyr's key components, including MQTT, DHCP. So essentially, the key features: it acquires an IP address using DHCP, brings up a secure MQTT connection using a secure socket connection, and then subscribes to user-defined topics. And there's threads that are dedicated to publishing temperature sensor data at regular intervals, along with dedicated threads for handling the incoming MQTT data. So this application shows what you can achieve quite quickly with Zephyr and when developing applications for 10BASE-T1L. Okay, so that brings us to the end of the presentation. I'll summarize with these key 3 points. So 10BASE-T1L single pair Ethernet is bringing long-range Ethernet to the edge with 10 megabit per second data rate. But however, enabling these edge devices with Ethernet connectivity, it goes beyond the transceiver, and software plays a really important role. And Zephyr is a great embedded software ecosystem to enable the development of edge-connected devices with Ethernet connectivity, thanks to its native TCP/IP networking stack, its security capabilities, and its real-time capabilities. So Zephyr is already SPE is already quite well supported within Zephyr. So I think if you're considering your next project and require robust, secure connectivity in the wired domain, why not consider 10BASE-T1L and Zephyr? Thank you very much. We also have a demo at the ADI booth showing a Zephyr with 10BASE-T1L, so it's booth E15. If you're interested, you can drop by for a conversation. Thank you.
Thank you, Jason. For folks in the room, if you have questions, I'll bring a mic over to you. If you're watching the live stream, please feel free to post questions in the chat, and I will repeat the question out so the speaker can hear it. Thanks.
Yeah, I was curious. A very good presentation, and I agree that single pair Ethernet is going to have a big play in many of these embedded markets. You talked about real-time and industrial. I'm curious how you see in the software stack, TSN is a big part of those stacks in this. How do you see Zephyr's support for TSN in there? I mean, TCP/IP is not exactly real-time, so I'm curious what your experience there is, and if there's more development needed in that area.
Yeah, it's a good question. I think TSN, yeah, you're right. It's kind of the next advancement, I think, in industrial Ethernet. So to the best of my knowledge, Zephyr doesn't have support for TSN connectivity. So generally speaking, I do think support for TSN is something that, in the context of Zephyr and ecosystems like Zephyr, it would require, I guess, a maintainers to kind of come together and look at how support for TSN could be done. from a software standpoint. It's not something I'm too familiar with, so I guess I don't want to comment in too much detail, as it's not something I'm very familiar with.
We don't have any questions on the chat. Thank you, Jason.
Thanks, everyone.